Good evening. Welcome to Krishna's classroom. Let us continue with the completion process of metric spaces. Now let us choose the following notation. Let X D be a metric space. Now we construct a new class of objects by constructing all Cauchy sequences of elements in X. Let us denote it by X tilde. Let X tilde, or let me use script X, denote the set of all Cauchy sequences that is X tilde, sorry, script X is defined as the sequences Xn. Xn belongs to X and so this is a new object we have constructed or fabricated out of the elements of X. Now by Cauchy sequence we mean the following, that we call Xn is Cauchy if for every epsilon positive there exists an n such that d of less than epsilon for every n greater than or equal to that's the definition of the Cauchy sequence. So you take such collection of sequences. In fact, we note that all convergent sequences the converse may not be. That there may be Cauchy sequences which are not convergent in X, or X is not big enough to accommodate the limit of all Cauchy sequences in X, like Q and R. So that's the example. So Q has Cauchy sequences which are not convergent. Whereas R has the property, in fact we have constructed R from Q when we have elaborately gone through the process, or at least reviewed the process very quickly to get a feeling of how these things come. So corresponding to x, suppose this is xb, we have now constructed a new class script x, which consists of all Cauchy sequences. Now, as we have explored Q and the Cauchy sequences of rational numbers, we have seen that the same or two different Cauchy sequences may converge to the same element. That's possible. In R, for instance, you can have several Cauchy sequences which converge to the same element, because in R has all Cauchy sequences convergent in it, and thus so we say R is complete. So you see that, but still, if you consider Cauchy sequences of elements in R, it's not a unique Cauchy sequence that is associated with a real number. Okay, there are several Cauchy sequences associated with the real, but then they are all related. That's what we have seen, because in those cases we have seen that two Cauchy sequences in R are related. So for instance, you take xn belonging to xn and yn are Cauchy sequences converging to the same real number, then we know that goes to 0. Okay, this follows from the fact that xn converges to x, yn converges to x, implies mod xn minus yn is less than or equal to mod xn which goes to 0. Therefore, mod xn minus yn goes to 0. So, if two Cauchy sequences converge to the same element, then we see that they are related. The relation is that this is the relation that you have xn related to yn if and only if so that's the sort of relationship that we want to work. What is the analog of that? You see that mod xn minus yn is going to be replaced by, this is going to be replaced in the general scenario by distance of, so wherever a modulus of something occurs, we replace it by the xy. So mod xy is replaced by the xy. So let us now build up the whole thing. Okay. So the problem that you encounter is this. In x tilde, some of these Cauchy sequences may be related and some of them may not be related in the sense in which we are going to take it up. Okay. So we shall see what kind of relation it is, and from our experience we see that this is likely to be a an equivalence relation, so that you can write up the whole X tilde or the script X as, I'm not talking about X tilde, but script X is now partitioned into equivalent classes. So work out that. So we have script X. This is contained in R. So on script X, script X consists of all Cauchy sequences of elements in capital X. We define a relation between elements as follows. We say that Xn is related to Yn to 0. That's a relation that we use. Now we look at the properties of this relation. We observe that, as we did observe in the case of sequences of rational numbers, see that Xn is related to Xn. Now this is trivial because Dxn for every n. So this relation is, therefore, this is reflexive. Now the second property that we observe is that Xn is related to Yn implies okay. Now that's quite easy because you see that Dxn Yn goes to 0 implies D because Dxn Yn equal to Dyn Xn. So you have the relation is symmetric. So to support, okay, the third property that we are looking forward to is the following. So the third property that we have is this. Xn related to Yn, Yn related to Zn implies Xn Zn. Now this follows for the property that Dxn is by the triangular inequality this is the triangular inequality. So this goes to 0, this goes to 0 means this goes to 0. That is the meaning of this. They are related. Implies as n tends to infinity. That is what you call the relation is transitive. So these three properties are there. To support all this, we want to make an observation. That is, if to support all this, we want to assert that if Xn is Cauchy, Yn is Cauchy, whether they are related to one another or not, D exists as a real number. Now we shall prove this, because this is essential to prove these statements, because we are assuming this, that it exists. Okay, so for all elements, or we can state the theorem. So let us prove this as a theorem. For each element elements changes x x. That is one result value because that supports everything. Then after that, everything else. So let us prove this theorem. So what we do is this. You know that we prove that is a Cauchy sequence of real numbers. Then it follows that completeness of that's a strategy. So all that we need to prove is that this is a Cauchy sequence in R. So we have to estimate it. So what do we do? So we claim that we shall estimate this. So we estimate P we estimate this. We estimate that this is less than or equal to So how does this come? In fact, you don't need modulus here, even otherwise this is true. Okay, let us see this, what is happening. Take a sequence. Suppose this is the sequence 7. We have another sequence yn, and these are Cauchy sequences. Okay. Now suppose this is the element xn, yn, then we are talking about the distance from xn to yn. This is d. Now you have, suppose this is xm. So this is yn. Now we want the difference between the distance between xn yn and xm yn. This is what we have computed. Okay. So we are working out the difference between these two. But what we do is, we have dxn yn is less than or equal to dxn xm and dxm yn and dy yn. Okay. And then you have these distances. Okay. So this is dxn xm. This is d. So you have dxn yn is less than or equal to, by triangular inequality, dxn xm plus dxm ym plus dym yn. So this part is majorizes this and then minus this. In fact, you don't need this at all, and then you are just subtracting from it. So what happens? In this case, these two cancel out. Okay, right? So you have an estimate of this. So we have the estimate of this. So we have d dxn xm plus dyn yn. This is the estimate that you have. Then we use the fact that this is a Cauchy sequence, xn is a Cauchy sequence, yn is a Cauchy sequence. So we have dxn yn is less than or equal to d now xn Cauchy implies given epsilon positive where x is n1 such that for every one d and there exists n2 such that so choose maximum of n1 and 2 this is satisfied, that is less than epsilon for every so see that is this is Cauchy R being complete. So that's the first thing that we now we just recall what we did. So we have introduced the relation Now what we do is that on on X Y is an equivalence now we call that is the relation. Okay. Now we have shown that is reflexive symmetric and transitive. That is an equivalence is an equivalence relation therefore what is that we can expect? The immediate consequence is that it induces a partition on X. So this proves it. Now X on X, the relation induces a partition. What is a partition? It is okay. What is a partition? The partition consists of so X is the disjoint union of equivalent of sets of Cauchy sequences. So what we have is this. This is X. Now this is divided into blocks. So you have Xn here and you have Yn also here. Then these two are related. So if you have a Zn here, Xn is not related to Zn. Okay, so this is how the partition goes. So every element of X, script X, is in one of the blocks, and these blocks are disjoint. Okay, so that's the breakup that you. So now let us introduce some notation. We introduce some notation, new notation. Just take care of. So we shall write let this is the block. So what you observe is that if xn is related to yn, then the block consisting of xn is the same as the block consisting of if is not related to Zn, then the intersection of the block consisting of xn that's the partition. And you have the whole of script x is equal to union of all these blocks. This is the partition that you now we can do certain things. Yes, let us give a name to this. We note the collection of all where have we started with? Started from xd, and then we looked at all Cauchy sequences of elements in x, which we designated by script x, and then we introduce a relation on that, and we found that that particular relation we have introduced is an equivalence relation, therefore it is partitioned and partitioned to equivalent classes, and therefore we designated by x tilde the equivalence class, the blocks of equivalence classes. Okay. So now we make some observations. Now we prove a little theorem. Let x and yn is such that goes to 0 as n tends to infinity. Then x. So we'll put this. Proof is very simple. We'll estimate this. Dyn, that makes sense, and this is less than or equal to and clearly this is dyn xn goes to 0. And dxn goes to 0 as, which implies d. So if you have a Cauchy sequence xn which converges to x, and you have another Cauchy sequence yn which lies closer to the sequence xn and eventually merges with it. That's the meaning of saying that dyn xn yn goes to 0 as n tends to t. Then yn also, the sequence yn converges to x. So that's a useful result that we shall require at some. Now we define or we prove another result. See, the idea is very simple. Suppose xn is a sequence. Xn and xn prime are sequences which merge eventually. So also yn and yn prime are sequences which merge eventually. In that case, what happens? See, the distance from xn to yn, the limit of that is the same as the limit of the distance from xn prime to yn. Let's prove this. This is eventually important in constructing a metric on x tilde. That's quite simple. See, because what you have is this, you have two sequences. This is one sequence, this is another sequence. So suppose this is xn and this is xn prime. So which merges eventually. And then you have xn prime, sorry, yn and yn prime. So what it says is this, suppose this is the element xn, this is xn. So this is the distance dxn prime. This is dxn xn. So you have dyn Now what it says is that suppose you consider this distance. What is this? This is d xn prime yn prime. This is the distance d dxn yn. So what happens eventually when xn goes to xn and xn prime go to the same point, or their distance will shrink, and the distance of these two also would shrink, which would mean that this would merge towards this. Okay, so this one would shrink down to get a distance, and this also shrinks down to the same distance. This is what this theorem says. That's quite easy to prove. There's nothing. So let us prove this. So we have dx and yn. This is less than or equal xn prime plus d xn prime yn prime plus d yn prime yn. This is using triangular integral. Okay. Now taking the limit as n tends to infinity, limit less than or equal to, this goes to 0. Okay, and this also goes to 0. Therefore, d now reversing the argument. We get d limit So together these two, so consequently limit n tending to infinity d xn yn Now, what is the significance of this theorem? That's what we want to explore. What does this theorem tell you? See, this theorem is significant in the following sense. Okay, what is the significance of this? So we have now x tilde, which is partitioned into equivalence classes, and on that we now use this theorem to see what emerges. So this is your and suppose this is and this suppose this is equally well to that and this is the same as because what we have is that means we have xn prime, therefore we have these two equally well qualified to designate this. So this is your block xn. And similarly we have and this means that this is the situation that we obtain. Now what you are writing here is, so let us designate D here. So also let us designate then D xn prime yn prime is E limit n tending to infinity B. So what this result in turn tells is that if the sequence xn and sequence xn prime represent the same block. So also yn and yn prime represent the same block. Then the distance between the block xn and the block yn and the distance between the block xn prime and the block yn prime are equal. So this is what we prove. Therefore, the distance is well defined. It is not dependent on what representation you use to designate the particular block. That's the outcome. So the above theorem assures that D is well defined and is independent of the Cauchy sequence. Designate. That is what it says. See, this is the same as this. This is the same as this. What it says is that if this condition is true and this condition is true, then these two are equal. Have to be equal. Should be equal. And that's what we have proved. These two are equal, therefore these two are equal. So irrespective of representations that you use. Okay. Brackets here. Okay. Okay. So this gives a good definition for the finite matrix on this class. So let us see now definition. On X theta, find still. So that's what we want to do. Okay. First of all, this is non-negative, really non-negative. Okay. It's the limit of a sequence of non-negative. Now, we have to prove two things, namely the symmetry is equal to 0 if then these two blocks are the same, or if and only if these two blocks are the same, and the triangular inequality is satisfied. Okay, so that's the theorem. So the theorem that we want to prove is that okay, let me use d tilde for it. Okay. Now all the ingredients are there now to prove this theorem. So we shall prove this next time. So that's a nice place to stop. So tomorrow most probably we will take up this proof of this theorem. Thank you very much.